All right, kitty, you gotta move. No, no. Okay, good morning, gang. Welcome back. Let me close my door here and get this kitty cat out. Oh, come on, big girl. I know, I love you. Okay, so last time we met the two comparison tests. The direct comparison test, which was built around inequalities, and the limit comparison test. Today, we're going to do a little more practice with the limit comparison test, and then we're going to learn about alternating series. I think I need to answer this. I'll give me just one moment. Hello. Sorry about that. Last time, we met the two comparison tests, the direct comparison test and the limit comparison test. Today, we're going to get a little bit more practice with the limit comparison test. And then we're going to learn about something called alternating series. Apologize if I'm a little bit frazzled. My car was in an accident this morning. Some lady just smacked right into the back while we were waiting to turn left, and she just didn't see us. So I'm a little shaken up, but everybody's okay. Is this disconnected? Ah, that's the problem. All right, that cat was doing all sorts of stuff. Let's try that. There we go. Okay. So this is MAC2312, section number 004, which is Calc 2. And the date today is the 4th of March, 2022. As I mentioned, today we're going to get a little bit more practice with the limit comparison test. And then we're going to learn about alternating series. Which is section 11.5. So the limit comparison test between the two comparison tests, direct comparison, one with the inequalities, and the limit comparison test, the limit comparison test is more versatile, right? Sometimes you can look at your series and you have a pretty good idea of what it's going to do, whether it should converge or diverge, because it reminds you of some other simpler series that you know well. But then when you go to try and build an inequality, the inequality doesn't work out. Either you can't find an inequality, or there is an inequality, but it points the wrong direction to be useful. There are a lot of series like that. And then there are some other series where it's not even immediately obvious what you're trying to compare to, where the limit comparison test is still going to be your buddy. So what I want to show you today are some more complicated examples with the limit comparison test, things where you might not see right away what it is you ought to compare to. So I'm going to start by saying, let's investigate the series S equals sigma n from 1 to infinity sine of 1 over n squared, whose first few terms are sine of 1, and then sine of 1/4, sine of 1/9. The next term would be the sine of 1/16, and so on. You may recall something called the small angle approximation. In Calc 1, when you learn about linear approximation, if you want to approximate the sine function near 0, you get this thing. The sine function is basically equal to its inside if the inside is close to 0. This is used a lot in physics, like when you learn about pendulums in Physics 1. You'll use this small angle approximation, and it is something that we do in Calc 1 as well. And this is kind of your hint here. This is what tells you what to expect from this series. So if you look over here, I've started writing out terms like the sine of 1/4, the sine of 1/9. The next term would be the sine of 1/16. The next term after that would be the sine of 1/25. The inside of the sine function there, the 1/n², that is getting small, right? 1/n² goes to 0 as n goes to infinity. So what this small angle approximation or linearization is telling you is that sine of 1/n² is basically the same as just 1/n². Maybe not for the first few terms, but after a while, once this 1/n² gets small, what this thing says is that sine of theta is basically equal to theta. So the sine of 1/n² is basically 1/n² if 1/n² is close to 0, i.e. if n is large. So when trying to think of a test for this series, this suggests that we should use some sort of comparison test, right? Definitely this series is not geometric, it's not telescoping, it's not a p-series, right? 1/n² on its own, that would be a p-series, but the sine of 1/n², not a p-series. It would be difficult to construct an inequality for this also, right? I don't know if sine of 1/n² is less than 1/n². I know it's very similar to 1/n², but I don't know if it's bigger or smaller. So a direct comparison would be hard. And for that reason, we are going to use a limit comparison test, LCT. And remember, as you're writing these things out, your first step should always be to tell your reader what you're doing. Let your reader know what test you're running. Your second step should be to write down whatever the object is in the test. So here, limit comparison test starts off by saying, you're going to calculate the number c equals limit n to infinity an over bn. And based on this, I'm going to pick bn to be 1/n². So this limit is limit n to infinity sine of 1/n² divided by 1/n². That's the an divided by the bn. And we had to pick the bn. If you just try to plug in infinity, which, good first thing to do, the top is going to be sine of 0 because 1/n² goes to 0. And the sine of 0 is 0. The bottom is also going to be 0, right? 1/n² that goes to 0 as n goes to infinity. So this looks like 0/0, which means we can use L'Hopital's rule. And it's nice to let your reader know what you're doing when you use L'Hopital's rule. You don't have to write it exactly like this, but I like to, just above the equal sign, put a little LH. L'Hopital's rule says take the derivative of the top and the derivative of the bottom separately, then you can try again. So upstairs, the derivative of sine of 1/n² would be cosine of 1/n² times the derivative of 1/n², which is -2/n cubed. If you want to see the work for that, right? 1/n² over n squared primed is n to the negative 2 primed is negative 2 n to the negative 3, which is negative 2 over n cubed. And then downstairs, I have that same derivative, right? The derivative of 1 over n squared. So it's also negative 2 over n cubed. And beautifully, these cancel. So I'm left with limit n to infinity cos of I'm so sorry, cos of 1 over n squared. Now, as n goes to infinity, the 1 over n squared goes to 0. So this is the cosine of 0, which is 1. I don't know what's cracking me up. All right. So what we've learned here is that if you choose Bn to be 1 over n squared and you calculate the limit from the limit comparison test, that number C comes out to 1. What does that tell me? What can I conclude? Let's see if anybody. Very good. Very good. Yeah. This means, so I say it like this, since C is positive and finite, the two series sigma an and sigma bn converge or diverge together, right? They do the same thing. Moreover, sigma bn, that's sigma n from 1 to infinity, 1 over n squared. Is this a convergent series or a divergent series? Very good. This is a convergent series. This is a convergent p-series because p here is equal to 2, which is bigger than 1. Thus, our series, sigma an, which is, I'll just say it like this, must also converge. So our series, that sigma sine 1 over n squared, that's a convergent series. Because according to the limit comparison test, it does the same thing as regular sigma 1 over n squared. Sigma 1 over n squared is convergent. This is the structure of all limit comparison problems. I don't mind saying that problems like this are problems I enjoy quite a bit and tend to show up on the exam. So if you see something like this, sigma sine 1 over n squared, something like that, then you want to run a limit comparison where Bn, you just choose Bn to be the thing on the inside. And the hint, the thing that tells you to do that, is this fact that sine theta is approximately theta for small values of theta. Any questions or comments on this guy? We don't know. Yeah. So the question, this is a good question. If Bn is larger and sigma Bn converges, that would tell me that sigma An converges. But do you know that this is larger? Do we know that 1 over n squared is bigger than sine of 1 over n squared? I don't know that. right? The inequality here would be hard to come up with. So that's the challenge, right? The challenge is actually building that inequality. Now, I think it may be true. Let me see here. But it's certainly not obvious. So it is true that sine, so the red curve is sine x and the blue is just x. So it is true that sine x is smaller than x, at least on this interval from like 0 to pi over 2, but it's far from obvious, right? Proving that is actually quite difficult. So I would not try a DCT here because it's very hard to come up with the inequality. And remember, when you use DCT, you need to justify your inequality. You need to tell me why it's true. There's a request to look at a homework problem. Sure. Yeah, we can take a quick peek at that. Number 15. And then I do have one other limit comparison problem in mind. So I'm going to move quite quickly through this. Or maybe we'll just use this one instead. Let's see what it is. Number 15. Ah, yeah, this is a great problem. Sure, I'd be happy to do this one. So same style thing, we'll say investigate the series S equals, we've got sigma n from 3 to infinity, 4 divided by n to the 1 plus 1 over n. So that an here, all right, we're just going to play with this for a minute and see if we can figure out what sort of test to use. Is n to the 1 plus 1 over n. What I would say is that this piece, this 1 over n here, this goes to 0 as n goes to infinity. So n to the 1 plus 1 over n is basically n to the 1 plus 0, or n, for large values of n. So in other words, this 4 over n to the 1 plus 1 over n is basically the same as 4 over n. And that gives us a good hint as to what to do. Again, there's no obvious inequality here. In fact, I think it's going to be the case that if the inequality you could prove between these two things, 4 over n would be larger, because this power being just a little bigger than 1 means this denominator is just a little bigger than this denominator, which means this thing is overall a little bit smaller than this thing. And that wouldn't help us. Showing that this thing is a little bit smaller than a divergent series is not helpful. So this is another great example of a limit comparison test problem. The workup here tells me that I should pick Bn to be, we can just do 1 over n. You could also do 4 over n if you wanted. Either one will work fine. And calculate C as the limit n goes to infinity, 4 divided by n to the 1 plus 1 over n over 1 over n. Now there is a subtlety here. We're going to run into a difficult limit. let me start breaking this out. And when we get to the step where we need the difficult limit, I'll tell you. First thing, fractions within fractions within fractions. Let's clean this up. That numerator stays the same, 4 over n to the 1 plus 1 over n times n over 1. Which is limit n to infinity for n divided by, now downstairs, n to the 1 plus 1 over n, that's n to the 1 times n to the 1 over n. You can cancel the n's, this guy. So we get lim n to infinity 4 divided by n to the 1 over n. This n to the 1 cancels with this n to the 1. But now the challenge is this guy, right? N to the 1 over n. So here's a little note. N to the 1 over n, that's the nth root of n. This is a tricky limit. The way you actually calculate this limit is by taking natural logs and then converting into an indeterminate ratio and then applying L'Hopital's rule. So you remember we saw a few of those back in 11.1, those really kind of nasty limits of sequences where you had to take the log and then do a bunch of algebra. This comes out to 1 by taking the ln, doing algebra, then L'Hopital, then exponentiating. This limit is one that I recommend you commit to memory. I'm not a big fan of saying memorize stuff, but this is one of those things because working it out each time it's needed, not a pleasant thing at all. You should work it out once, but then remember it. So here, back in the workflow for our problem, 4 divided by n to the 1 over n is going to become 4 divided by 1 because this denominator goes to 1. So this is just going to be 4. And now we can finish up the problem. Since 0 is less than c is less than infinity, right? 4 is positive and finite. The series sigma an and sigma bn converge or diverge together. Moreover, sigma bn is sigma 1 over n. Is this series convergent or divergent? Sigma 1 over n. Very good. This is a divergent series. It's the harmonic series. Or you could say it's a P series with p equal to 1, which is less than or equal to 1. So my series sigma an and the series sigma bn, which is the harmonic series, do the same thing, plus our series sigma an, which is sigma n from 1 to infinity, 4 divided by n to the 1 plus 1 over n, also diverges. Very cool. So that blue box limit up there, that is something you should work out. All right, if you've never worked that one out before, it's something you should take the time to work out. It's just like the e to the ab limit that you had in your homework. Same sort of thing. It's an indeterminate power. All right, you get infinity to the 0 if you just plug in, and that's an indeterminate power. Questions on this guy? Okay. So our series, sigma 4 over n to the 1 plus 1 over n, this series diverges because when you do a limit comparison with the series sigma 1 over n, limit comparison says calculate the limit as n goes to infinity of an over bn. If this limit comes out positive and finite, then the two series do the same thing. So that limit came out to 4. So since that limit is positive and finite, the series sigma an and sigma bn, right, my series and the series we're comparing to, do the same thing. They converge or diverge together. And then we can say, well, that series sigma bn, that's the harmonic series. That's sigma 1 over n. I know that that series diverges. You can either say it's the harmonic series, which we proved to diverge, or you can observe that it's a p series where p is equal to 1. And you know, p series only converge if p is strictly bigger than 1. So this guy diverges, and these two series do the same thing. Therefore, our series must also diverge. That's the logic. Cool. Right. We'll grab a little bit of water, and we're going to talk about the alternating series tests. What do you say, baby? Yeah. All right. Oh, we got a little help up here. Kitty cat, I love you. I know you like this spot. I know that. I know that. I love you. It's gonna be okay, but you can't be there right now. All right. I'm sorry. All righty. So I'd like to draw your attention to a fact that may not have occurred to you so far. Oh, another good question there in chat. Does the small angle approximation work for cosine or tangent? No for cosine, yes for tangent. Yeah, if theta is small, then the cosine of theta is going to be about 1, right? Because cosine of 0 is 1. But tangent is sine over cosine. So tangent, if theta is small, tangent of theta is like sine theta over cos theta. Sine theta is approximately theta. Cos theta is approximately 1. So yes for tangent, but no for cosine. All right. A fact you may not have noticed so far all of our series, except for some geometric series, have positive terms. Right? If you look back at your tests, the convergence tests we have so far, the integral test says that the corresponding function needs to be positive, continuous and decreasing. But positivity means the series has positive terms. Direct comparison test says 0 is less than an is less than bn. Well, that means both an and bn are bigger than 0, both positive. The limit comparison test says if sigma an and sigma bn are series with positive terms, then blah, 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 blah. All of our series and all of our convergence tests only work for positive term series. So what do we do if I have a series where the terms are not all positive? There are certainly a lot of series like that, and the most common ones are alternating series. So what we're going to develop here is a test for a series where half the terms are positive and half the terms are negative. First, we need a definition. A series is called alternating if the terms change sign every time n increases by 1. The usual way of writing these is sigma -1 to the n times bn. And that could be summed from 0 or 1 or 2. And if you just start writing this out, -1 to the 0 is +1. So this would be +1 times b0. When n is 1, you have -1 to the 1, which is negative. So you have minus b1. When n is equal to 2, -1 squared is positive. So this would be plus b2, and then minus b3, and plus b4, and minus b5, and on and on and on like that. Definitely, this is not the only way to write an alternating series. You will also see stuff like sigma n from 1 to infinity, -1 to the n plus 1 times something. And this would look like b1 minus b2 plus b3 minus b4 plus b5, and so on. So you see what's happening here, right? The terms go positive, negative, positive, negative, positive, negative, positive, negative. Any series where the terms go from positive to negative every time you go up 1 is called an alternating series. These would be it's important that the bn's here are positive, because if, say, b2 was negative, then this term wouldn't actually be negative, right? Negative, negative would make it positive. Alternating series like these, have a much easier time converging than series of positive terms. With a series of positive terms, the partial sums always form an increasing sequence, because when you add one more term, you're adding something positive. That just makes the partial sums bigger and bigger and bigger. And what we've seen is that for a series of positive terms to converge, we need the terms to go to 0 really fast. Not just go to 0, but go to 0 fast. Fast enough that adding the next term and the next term and the next term doesn't make the sequence of partial sums blow up to infinity. With an alternating series, every other term subtracts something. So the partial sums are not necessarily an increasing sequence. This makes it much easier for them to converge because every term isn't just like stacking on more and more and more shit. Term adds a little bit, the next term subtracts a little bit, next term adds a little bit, next term subtracts a little bit. And these things slow down the growth of the partial sum, making it easier for the series to converge. So much so that the following is true. This is called the alternating series test. And if you have a special place in your notes for convergence tests, this is the next one you need to write down. If you're making flashcards for your convergence tests, you need to make a flashcard for this. It says if the alternating series, and I'm just going to write it like that first way, sigma -1 to the n times bn satisfies two conditions. First, that the sequence bn is decreasing. So, right, the piece besides the -1 to the n, if that is a decreasing sequence and the limit as n goes to infinity of the bn's is 0, then the series converges. And this should be kind of shocking. We've seen lots of series where the terms are decreasing and go to 0, but the series still diverges, right? Like sigma 1 over n, or sigma 1 over the square root of n. Those are all series where the terms are decreasing and go to 0, but the series still diverges. And what this test is saying is that if you had an alternating series like that, then those would converge. And I'm going to show you some examples in a moment, but I do want to go over the proof of this theorem because the proof is quite nice. The other thing that is in this section, by the way, is an estimation theorem. There are several estimation theorems in the textbook. There was one in 11.3 that we didn't discuss. And there will be one in 11.10 that you are not going to be held responsible for. But the estimation theorem from this section, you will be tested on. So we'll go over that. But first, we're going to prove this theorem, and then we're going to look at an example. Let S be the alternating series and 0 to infinity, -1 to the n times bn. And suppose that the bn's are decreasing with limit 0. So suppose that those two conditions from the alternating series test are satisfied. Then what we want to show is the series converges. Right? If the test is correct, then these two things being true should be enough for us to prove that the series converges. Because none of our other convergence tests can be applied, the only way to argue that the series converges is to start working with the partial sums. So S has partial sums. I'm just going to write out the first few. S0 would just be B0. S1 would be B0 minus B1. S2 would be B0 minus B1 plus B2. S3 is B0 minus B1 plus B2 minus B3, and it keeps going like that. I'm going to plot these partial sums on a number line. All right, so here's the number line. And I'll just say B0 is over here somewhere. So that's S0. To go from B0 to to go from S0 to S1, well, what's the difference? S0 is just B0. S1 is B0 minus B1. So we're going to move to the left by B1 units. So from over here, if I subtract B1, that means I'm moving to the left by B1 units. Then right here, that's S1. To go from S1 to S2, to go from this partial sum to this partial sum, well, it's B0 minus B1, B0 minus B1, plus B2. So I'm going to go to the right by B2 units. And I want to ask you, is that going to leave me over here or over here? We know we have to go to the right from here. So we're going to be somewhere over in this region here. But the question is it going to be in here or out here? So think carefully about this. We need to think about one of the assumptions we've made about the sequence Bn. What do we know about Bn? Good, decreasing. Very good. Because the Bn's are decreasing, if you think about what that means, this means that Bn plus 1 is always less than Bn. Right? So B1 is smaller than B0. B2 is smaller than B1. B3 is smaller than B2. So because B2 is smaller than B1, I know I'm going to the right, but I'm not going to go any further than here, right? I'm adding B2. The length of this arrow is B1. The length of this arrow is B2. And I know that B2 is smaller than B1. So the second arrow down here has to be shorter than the first arrow up here. So that tells me that S2 is right here, somewhere inside, somewhere between S0 and S1. And that's the big idea. And then we keep doing this to go from S2 to S3, right? S2 to S3, you've got B0 minus B1 plus B2 minus B3. So we're going to go back to the left now. We're subtracting. And because B3 is smaller than B2, we're going to stay inside. We're going to come back this way, but the length of this arrow is B3, the length of this arrow is B2, and I know that B3 is smaller than B2. So that means that S3 has to be somewhere in here. And if you think about what this is going to lead to, right, to go from S3 to S4, we would add B4. B4 has to be smaller than B3 because the Bn's are decreasing. That means that S4 has to be in here. So what's happening? We go S1, S0, S1, S2, S3, S4. We're moving back and forth and we're coming in here. Like S5, S6, S7, S8, S9, S10. We're going to pile up on some point in here. because the bn's have limit 0, the length of these arrows will eventually go to 0. So we will actually have an accumulation point in here, and that is S. In other words, the sequence of partial sums, Sn, must converge. And if the Sn's converge, that means they have a finite limit. And that is the definition of the infinite series converging. So I would say by this nesting behavior, and the fact that the limit as little n goes to infinity of Bn is 0, we see that the sequence Sn must be convergent. But that is precisely what it means to say the series S is a convergent series, right? A series converges if its partial sums have a finite limit. And because of this nesting behavior, the partial sums have a finite limit. Therefore, the series converges. That's the proof. Very pretty, right? I love this proof. So this is why it's so much easier for an alternating series to converge than a series of positive terms, because every other term takes a little away, then gives a little, then takes a little away, then gives a little, then takes a little away, then gives a little. So it means that it's a lot easier for the sequence of partial sums here to be a convergent sequence. And the sequence of partial sums being convergent is what it means for the series to be convergent. Beautiful proof. Okay. Let me show you how to use this. Let's take a look at an example of an alternating series and see if we can prove that it converges using the alternating series test. Before I move away, are there any questions on this proof? One interesting fact, you notice this doesn't say anywhere that the series would diverge. The alternating series test can never tell you that a series diverges. It can only tell you that a series converges. I'll come back to that in a minute. Let's investigate the series S equals sigma n from 1 to infinity, -1 to the n plus 1 over n. This is a quite famous series. It has a name. And to see what that is, let's start writing out some terms. When n is 1, we get -1 squared over 1. -1 squared is 1, so this is just 1. When n is 2, we get -1 cubed over 2. So that's -1/2 or -1/2. When n is 3, we get -1 to the 4 over 3. So that's +1/3. The term after that would be -1/4, then +1/5, then -1/6, and so on. What series does this remind you of? Yeah, this is very similar to the harmonic series. It's the harmonic series. It's just been made to alternate. That -1 to the n plus 1 up there makes it into an alternating series. This is called the alternating harmonic series. We know that the regular harmonic series diverges. Let's see about this guy. So here comes the solution. S is sigma n from 1 to infinity. I can rewrite this as -1 to the n plus 1 times 1 over n. So Bn here is 1 over n. This is an alternating series, where the Bn's are just 1 over n. So we're going to run the alternating series test, which I'll abbreviate as AST. And you should always tell your reader what you're doing. We want to check those two conditions. Is Bn decreasing? And is the limit as n goes to infinity of Bn equal to 0? We need to check these two things. Well, if you take those Bn's and you prime them, you take the derivative, that's the derivative of 1 over n. 1 over n is n to the -1, so this is going to be negative n to the -2, that's -1 over n squared. And yeah, that's negative. For all n greater than or equal to 1, thus, yeah, Bn is decreasing. So it's a checkaroonie. Is the limit of the Bn 0? Well, limit as n goes to infinity of Bn, that's the limit as n goes to infinity of 1 over n, which is 1 over infinity, which, yeah, is indeed 0. So that's a double checkaroonie. So according to the alternating series test, the series converges. Done. And you see, this is actually a pretty easy test to use. Right? You just have to check these two things. Sometimes showing something to be decreasing can be a bit of a pain, but it's not that bad. You know, you take the derivative and show that the derivative is negative, or you can show that that inequality, Bn plus 1 less than Bn, is true for all n. That's usually a little bit more work. But either way, you do get here that the Bn's are decreasing and that the limit of the Bn's is 0. And just from those two things, we see that the series converges. I want to make a little comment. AST will never tell you that a series diverges. If one of those two conditions is not met, if the limit as n goes to infinity of Bn is not 0, or the sequence Bn is not decreasing, then AST is inconclusive. Which means you need to try something else. You need to try a different test. But I just want, it's a common mistake. I see it a lot. People say, oh, one of these two things doesn't work out, therefore the series diverges by AST. That's wrong. That's not correct. AST can never tell you that a series diverges. It's just not a part of the theorem, right? The theorem says if these two things are true, then the series must converge. Nowhere in there does it say if these things are not true, then the series diverges, right? Here's the statement. Here's the statement, right? If these two things are true, then the series converges. That's it. There's nothing in there that says if not, the series diverges. So what do we do? What do we do if we run into a series where one of those things isn't true? Let me show you an example. Here's an alternating series. N squared divided by n squared plus 9. Oh, yeah, we can go back for a second. Don't see anywhere we say AST. Oh, is inconclusive. Sorry, yeah, it's down here. Inconclusive. Okay. Okay. So let's see what happens if I try to run AST on this. This is an alternating series. S is alternating. And the BNs here are n squared over n squared plus 9. So we'll run AST, and we're going to just check how the BN's decreasing. Well, again, I'll do it with the derivative. Bn primed this is a quotient rule thing. So bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And if you distribute everything out here, what do we get? I've got 2n times n squared. That's 2n cubed. Plus 9 times 2n is 18n. Minus 2n times n squared is minus 2n cubed. All divided by, oh, sorry, this should be squared down here. N squared plus 9 all squared. The 2n cubes eat each other up, and you get 18n over n squared plus 9 all squared. Well, this actually isn't negative, is it? This is positive. So this, which is positive for all n greater than or equal to 0. That's a problem. Also, if you check the limit as n goes to infinity of bn here is limit n to infinity n squared over n squared plus 9. If you divide top and bottom by n squared, renormalize, and this is 1 over 1 plus 9 over n squared. The 9 over n squared goes to 0 as n goes to infinity. So this is 1 over 1 plus 0 when you take the limit, which is 1, which is not 0. So the series fails both conditions. All right, I should say so. So bn increasing. And here this is not equal to 0. So we got problems. But all AST says here AST just shrugs its shoulders and says, I don't know, man. I got nothing for you. I can tell you if the bn's were decreasing and if the limit was 0 that the series converges. But here those things aren't true, so I don't fucking know what to say. So we need to think of some other way to approach this problem besides the alternating series test. And the hint here comes from the second item. I can't use direct comparison because this is not a series of positive terms. Can't use limit comparison because this is not a series of positive terms. I can't use the integral test because the function we would get here is not positive. So those tests are all out. The bottom doesn't factor, so there's no chance of this being telescoping. And it sure as shit isn't geometric. N squared over n squared plus 9 is not some constant to the n. That only leaves one thing. Which one of our convergence tests have I not mentioned so far in this discussion? What was the very first convergence test we learned? TFD. Yeah. Yep, TFD will work here. And the hint that TFD will work here is that the limit of the BNs is not 0. So BN and AN, they're not the same thing, right? BN is like the non-alternating part of the terms. So this piece is BN. This whole thing is AN. And TFD says, calculate the limit as n goes to infinity of AN. If that's not 0, then the series must diverge. And this will work here because the limit as n goes to infinity of AN is the limit as n goes to infinity of negative 1 to the n times n squared over n squared plus 9. There's a few ways to attack this limit. We know that AN goes to 0 if and only if the absolute value of AN goes to 0. That was one of our theorems from 11.1. Or you can say that this piece, we just showed that this piece goes to 1. So what we really have here is limit n to infinity, negative 1 to the n times 1. Which is just the limit as n goes to infinity of negative 1 to the n. And what is that limit? What is the limit as n goes to infinity of -1 to the n? Good. D does not exist. And that's different from being 0, isn't it? So by the test for divergence, the series S equals sigma n from 0 to infinity, -1 to the n times n squared over n squared plus 9 diverges by T F D. That is how you show that the series diverges. So again, just for emphasis, if a series fails AST, if a series fails the alternating series test, we don't learn anything. That's inconclusive. So you should try something else. TFD is usually the test you're going to use because none of the other tests apply to alternating series. Now, we will have other tests later that you could apply, the root test and the ratio test. But if your alternating series fails AST because the limit of the BNs is not 0, then automatically the series fails TFD because AN is -1 to the n times BN. And if the BNs don't go to 0, then AN can't possibly go to 0. Right? If your BNs go to 5, then this would be a 5. If your BNs go to pi, then this would be a pi. -1 to the n times some number, some constant, that limit's always going to be DNE. So if your series fails the alternating series test, you should try the test for divergence next. That will usually do the job. But don't make the mistake of saying that because your series fails AST, the series diverges. That's not true. There are plenty of alternating series where the BNs aren't decreasing, but the series still converges. That happens all the time. So failing AST does not automatically mean the series diverges. Okay. That's enough on this. Any questions on this example? Enough prattling from me, at least. Okay. The last thing we need to talk about is something called the estimation theorem for alternating series. And I'm going to come back to this picture we drew when we were proving the alternating series test. First, let me just share with you the theorem. Estimation theorems, what they do is so it's very hard to sum series, right? To find what the series adds up to is very, very hard. We can only do it for geometric series and telescoping series. All the other series don't ask you for the sum, right? They just ask you to tell me whether the series converges or diverges. Maybe they ask you to approximate the series using a partial sum, right? Write out the first 10 partial sums and approximate the series. But in general, finding the sum of a series is very, very difficult to do. What this theorem does is allows us to estimate the sum with a known error, but only for alternating series. Now, it turns out that like 80% of the cool series are alternating series. So it's not as much of a restriction as you might think. Again, there are other estimation theorems in the book. This is the only one I'm going to test you on. So you do need to learn what this theorem says and how to use it. Here's what the theorem says. If S equals sigma -1 to the n bn, or any other alternating series, is a convergent alternating series, then the error in the nth partial sum, what this is less than, or less than or equal to b sub n plus 1. You're going to need to think about this object a little bit. S is the sum of the series. It's the value of the whole infinite series. Sn is the nth partial sum of the series. When you subtract them, what that tells you is how far Sn is from S. So the absolute value of S minus Sn, this is the error or difference or distance from S to Sn. It's how off Sn is as an approximation to S. So if I want to get an idea for the value of an infinite series, obviously I can't add up all the terms. That's hard. There's infinite many of them. But if I want to get a rough idea, I could just look at a partial sum. I could take like a big long partial sum, maybe the first 50 terms, and say, okay, well, the full infinite series has to be pretty close to that. And I can add that up. What this theorem allows us to do is to be quantitative about the error. So if I say approximate this sum with error less than 0.01, we can do that now. The theorem guarantees that the error is smaller than the next term of the series. That's what it says. It says that the error in the nth partial sum is smaller than the next term of the series. So if I want the error to be less than some amount, then I can set this thing less than that amount and solve for n. That will tell me how many terms I need to use in the nth partial sum to approximate the series with that error or better. The proof is this. So let me see here, proof. It's very fast. S minus Sn is the distance from S to Sn. So here's S. Let's look at the distance from S to S2. All right, we go S0, S1, S2, S3, S4, S5, S6, S7, S8, S9, S10, blah, blah, blah. Right? Here's the distance from S2 to S. This is like if capital N was 2. How far apart are they? Well, they're this much apart. Can I say exactly what that is? No. But if you look at the distance from S2 to S3, that distance is bigger than the distance from S2 to S, because every time I go from S2 to S3 or S3 to S4, I jump over S. That's because of this nesting, this alternating thing. Going from S0 to S1, I jump over S, which means that the distance from here to here is less than the distance from here to here. Or looking from S2 to S, the distance from here to here is less than the distance from here to here. And that is a known distance. The distance from S2 to S3 is B3. All right, we're going to the left, so there's a minus here. But if you're just asking how far is it, the distance is B3. The distance from S3 to S, if you wanted to look at that, that's here to here. Because S is between S3 and S4, the distance from S3 to S has to be less than the distance from S3 to S4. Well, that's B4. So this is always going to be less than or equal to the distance from Sn plus 1 to Sn. Because S lives between Sn and Sn plus 1. Because S is between Sn and Sn plus 1, we know that the distance from S to Sn is less than the distance from Sn plus 1 to Sn. Right? The distance from S2 to S is less than the distance from S2 to S3. Now that distance is exactly, what's the distance from S2 to S3? It's B3. What's the distance from S3 to S4? It's B4. That distance is exactly Bn plus 1. And that's it, lads and ladies. That's the proof. Blam. Short and sweet. So how do we use it? Well, you take some series that an alternating series that you know converges, and you're going to set Bn plus 1 less than the error you want. So let's say estimate the series we just worked with, the alternating harmonic series, sigma n from 1 to infinity, -1 to the n plus 1 over n, with error less than, let's say, 0.001. That means that the first decimal is guaranteed correct, the second decimal is guaranteed correct, and the third decimal could be off by 1. Okay, by the estimation theorem, S minus Sn is less than Bn plus 1. So it suffices to solve the inequality if I want the error to be smaller than 0.01, and I know the error is smaller than Bn plus 1, I can set Bn plus 1 less than 0.001 and solve for n. This will tell me how many terms I need. All right, well, Bn is 1 over n, so Bn plus 1 is 1 over n plus 1. 0.001 is just 0.001. And we can write the right-hand side as a fraction also. So this gives me 1 over n plus 1 is less than, let's see, this would be 1/10, 100th, 1,000th. So 1 over 1,000. Now, if you cross multiply, you get 1,000 is less than n plus 1. In other words, $999 is less than capital N. So I can use for capital N any number greater than 999, and the error in the capital Nth partial sum will be guaranteed less than 0.01. So we can use n equals 1,000, right? That's the first integer bigger than 999 to estimate our series with error less than 0.001. What do you order? Maybe some. Let's see what we actually get. Let's see what we actually get. So let's use n equals 1,000. That means I'm looking at S 1,000, which is the sum from n equals 1. We use 1, right? Yeah, 1 to 1,000 of -1 to the n plus 1 over n. This would take me quite a while to add up by hand, right? This is 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, all the way out to 1 over 1,000. I'm lazy. No, thank you. I'm not doing that by hand. That's too many terms. But I can tell Wolfram to sum -1 to the n plus 1 divided by n from n equals 1 to n equals 1,000. Okay, here it is as a fraction. Fuck that noise. As a decimal, we get 0.6926 blah blah blah. Anybody want to guess what this number is? I've made a few jokes about it. It's the natural log of 2. The full value of the series here is the natural log of 2. Right, 0.6931. So we're off by a tiny little bit, but the error is less than 0.001, right? The first 2 decimal places are perfect, and in the third decimal place we have a 2. The correct third decimal place would be a 3. So the error is about 0.001. So, and we know, because I say so, I'll tell you why later, we know that the full value of the series S is the natural log of 2. I'll be able to explain this to you after we learn about Taylor series. And if you write this out as a decimal, it's 0.693, I think 31 is next, right? Yeah, 3147. Blah, blah, blah. So the error is indeed less than 0.01. That's what we were hoping for. You need to know how to use this theorem. There will be a question on your test where you need to use this theorem to tell me how many terms you need to approximate a series with a specific error. And there are some problems in your homework that ask you to do this. You can practice it there. Please practice it as I've shown you here so that you're ready to do it on the test. It's not that hard, I promise. You just set bn plus 1 less than your desired error. Solve for n. Okay, that's all we have time for today. So in conclusion, I just want to say a few things. Your test 2, is going to be the week we get back from spring break. It'll be that Friday, because I think giving you a test on that Monday is sadistic and evil. And also because there's some more material we need to talk about. I haven't shown you guys the root test or the ratio test yet. I'm going to go ahead and publish your study guide today. And that study guide is going to have stuff from 7.8, 11.1, 11.2, 11.3, 11.4, 11.5, and 11.6. There'll also be some stuff from 11.7. 11.7 doesn't have any new material in it. It's just a bunch of combinations of problems from the previous sections on series. So when we get back, I'm going to teach you 11.6, which is the root test and the ratio test. You won't be able to solve those problems yet, unless you choose to look up videos, study them independently. That's up to you, but I won't be expecting you to do that. I will be expecting you to spend some time over break working on the study guide. Please do that. Please do not spend the whole 9 days doing zero mathematics. It will fuck you up so bad. I swear, it's not good. Doing the test after break is forgiving in the sense that it gives you a little bit more time to study, but it's bad in the sense that it gives you time to forget stuff. And if you don't practice this over the weekend, you will forget it. Ask anybody who speaks more than one language. If you don't practice that second language or third language, then the skills degrade very, very quickly. That's true of mathematics as well. So please, over spring break, work on the study guide just a little bit, maybe 2 or 3 days, spend an hour or something solving some problems. I will be responding to emails over break. I cleared out all the extension requests yesterday, pushing everything to the 14th. So everything, if you have an extension request in, you're good to work on that shit all the way through to next Monday. And I encourage you to do that as well. Okay, so if you need help with anything, come see me. I have an office hour today from 1 to 2. I'll be doing some makeup tests. So the office hour, we're going to have to move into breakout rooms. And then over break, make sure you study a little bit. Mohan, yes. So on the test, I would be asking you for the value of n. I wouldn't ask you to do this computation because obviously you won't have access to a computer to do this. So on the test, when I give you a problem like this, it will say, tell me the number of terms needed to approximate such and such series with error less than something or other. And you will just need to come up with the value of n. Any other questions before I wrap things up here? Okay, then have a good break. Please be safe. Someone hit my wife in the car this morning, as I told you. People are already getting sloppy out there. Don't be sloppy. Please take care of yourself. Be safe. Enjoy the break. Study a little bit of math so you don't forget everything, but also do what you need to do to recharge and have a good time. Take care, guys.